Very warm welcome. In this video, we will be looking into the concept of transaction management in MySQL, which is MongoDB and Cassandra. I'm Rajeshri, Assistant Professor from the Department of Computer Science and Engineering. So now let's have an introduction to what is meant by a database transaction. Now a transaction is a single unit of work that either fully completes or has no effect ensuring data integrity. Now this is a sequence of database operation that include a read, write, update as well delete treated as one single logical unit. The main goal is to maintain the database consistency, integrity, especially under concurrent access and system failure. Now the traditional model for transaction has a strict set of properties adhered to by most relational databases, preferably SQL, which is nothing but the ACID property that refers to atomicity, consistency, isolation, and durability. Now, however, the NoSQL trade-offs, like many NoSQL databases like Cassandra, relax one or more of the ACID property to achieve better performance and availability that is mentioned by the CAP theorem. Now, what is meant by a transaction boundary? That is defined by a begin transaction, a set of statements, and either a commit, which is a success, or a rollback, a failure. Now, concurrency control mechanisms like locking used to manage simultaneous transaction without causing data corruption. Then ACID property, the SQL standard. Atomicity, all or nothing, ensures a transaction is treated as an indivisible unit. Either all changes are applied or none. That is a complete commit or a full rollback. Consistency or otherwise the rules preservation guarantees that a transaction moves the database from one valid state to the other, upholding all constraints, that's preferably the primary key, the foreign key, the unique key constraint, etc. Then isolation, which is nothing but the independent execution, ensures current transaction execute as if they were running sequentially, preventing from interference with one each other data changes. Durability, persistence, guarantees that once a transaction is successfully completed or committed, the changes are permanent and survive subsequent system crashes, power loss, or restart. Then implementation, durability is typically ensured by write-ahead logging, where the changes are recorded to a log file before being applied to the data file. Now, strict ACID compliance often involves higher overhead from these locking and logging mechanisms, which can impact the performance and horizontal scalability. Transaction isolation levels in SQL. First is serializability, which is the highest form of isolation level, guarantees transaction that execute sequentially, prevent dirty read, non-repeatable read, and phantom read. Repeatable read prevents dirty read and non-repeatable read, but phantom read, that is new rows appearing in the result set, are still possible. Now read committed, which is nothing but the common default, prevents dirty read, that means reading uncommitted data. Other transaction changes are only visible after they commit. Then read uncommitted, which is the lowest level, allows dirty read, meaning a transaction can see changes made by another transaction that has not committed yet. Dirty read, reading data that another transaction has modified but not yet committed. If modifying transaction rolls back, the read was dirty. The non-repeatable read, reading the same row twice within a transaction and getting different values because another committed transaction has modified it in between. Then transaction management in MongoDB, single document atomicity, all operations document are atomic by default, so which is a fundamental unit. Then this has introduced the capability to execute operations across multiple documents collection, even shared as single ACID transaction. Then multi-document transaction in MongoDB provides full ACID guarantees similar to relational databases, but they operate on the document data level. Then isolation implementation is done by using snapshot isolation, provides consistent view. Preferred model, the recommended practice is to embed the related data to keep the transaction as a single document. However, the limitations are this gives a high overhead and also takes a maximum execution time. The best practice is to modify less than 1000 documents. Then what is meant by a multi-document transaction detail? One is session-based, which is initiated within a client session using a start session, following the familiar start transaction and a commit transaction. Distributed transaction supported by multi-document transaction since MongoDB 4.2. Then atomicity, that all write operations will be applied, or if any fail, the operations will be rolled back. Durability, the changes are durably persisted by using a commit transaction leveraging the replica's write ahead log. Then MongoDB transaction use isolation that is comparable to serializable for the data they read. Then concurrency, by acquiring necessary locks on the document, prevents conflicting writes. Then transaction management in Cassandra. Here we don't have any full asset. This is designed for high availability and linear scale, adopting the base model and providing a lighter form of transaction support. So here atomicity is guaranteed on a low level within a single partition, a single row update, all or nothing. Then consistency is highly tunable, and also the transactions are lightweight, uses the if clause in SQL, that is insert if not exist or update if condition to achieve compare and set semantics. Linearizable consistency, this provides the strongest form ensuring a global order of operation but with a significant performance cost. Then isolation is guaranteed at the row level. Update to a row is not visible until the update is complete. Finally, a comparison of the consistency model, asset versus base. Asset, atomicity, consistency, isolation, durability, prioritizes consistency and integrity over availability. Base, basically available, soft state and eventually consistency, prioritizes availability and partition tolerance over immediate consistency. Cap theorem states a distributed system that only guarantees two of the three properties, consistency, availability, and partition tolerance. SQL choice, typically consistency and partition tolerant, sacrificing some availability during the network partition or node failure. Cassandra's choice, typically available and partition tolerant, sacrificing immediate consistency for high availability and constant uptime. Eventual consistency, the system guarantees if no new updates are made, all data copies will eventually converge to the same consistent value. Then finally, the distributed transaction has its own challenges. The first is all about the two-phase commit, a common but often avoided protocol where the nodes vote on a transaction and then commit or abort together. This is blocking and slow. Sharding complexity. Distributing data, that is sharding, increases the performance, breaks the atomicity guarantee, requiring a multi-phase commit protocol. Network partition, a very critical challenge where network failure prevents the node from communicating. Isolation breakdown, difficulty in maintaining a global lock or a snapshot across disparate nodes leads to difficult to detect anomalies. Saga pattern, a non-ACID alternate in microservice architecture, use a sequence of local transaction with compensation actions to undo the previous work upon failure. MongoDB solution uses a sophisticated protocol based on wrapped consensus algorithm to coordinate the multi-document transaction across the replica sets and shards. Cassandra's alternate generally avoids multi-partition transaction, pushing the complexity to the application layer to manage data denormalization and eventual consistency. So what can be the best practice? Use SQL for complex transaction when strict ACID property guarantees complex and multi-table. Optimize MongoDB with embedding. For MongoDB, design the schema to use embedded documents to leverage the fast atomic single document operation. Reverse the MongoDB multi-document. Only one use MongoDB's multi-document transaction when necessary because they introduce performance overhead and latency. Cassandra, embrace denormalization. Denormalize the data and use a single row partition to support high-speed query. True consistency. Carefully choose consistency level, read-write, balancing the need of data freshness against availability and latency. Finally, avoid 2PC in distributed system. Modern distributed system, including MongoDB, prefer non-blocking algorithms over the traditional two-phase commit protocol. Thank you.